All right, so here is problem 136, page 382, the last problem in homework set 25 that we're going to make a video for. It is strangely the sister to your problem 136, page 382. If you're paying attention, I'm doing a problem for you here. And I won't even pose the problem. This kind of falls into the category of let me show you something here that we haven't talked about before. So here's a Cartesian coordinate system, xy. There's a line running through it, and that line is in slope-intercept form, y equals mx plus b. And so you know that m is the slope of the line. And you know that b is the y coordinate of the y-intercept. Don't care so much about that. We do care about the fact that m is the slope of the line. So let me do this. Let me draw a unit circle centered on that intersection between the line and the x-axis. Right? So it's a unit circle that makes this length right here 1, and more importantly, it introduces this little triangle right here. Yeah. And we're going to focus on this little triangle with a subtended angle of theta. If that is angle theta and this is a unit circle, then that little height there is the sine of theta, and that little length there is the cosine of theta. All good. Let's calculate the slope of this line from the basic definition. M is equal to the rise over the run. And I'm going to compute that rise over run as I move from this point on the line to this point on the line. Focus just on the line for a second. I could go from here to here. I could go from there to there, but instead I'm going to go from here to here. And in doing so, look, the rise as I go from here to here is this. This point has a y value of 0. The y value of this point is sine theta. Yeah, can I just draw the horizontal to make that painfully clear? There it is. That's sine theta. Okay? And likewise, so the rise is sine theta. The run is cosine theta. So the basic definition of the slope of that line is the rise over run. We've just shown that the rise over the run is sine theta over cosine theta, which is equal to the tangent of theta. So why is that important? Because it shows that the slope, what it does is introduces trigonometry into analytical geometry. If we haven't done that already, this definitely does it. The slope of a line, m, is the tangent. Let me just write it out like this. It is the tangent of the angle that the line makes with a horizontal. I don't know why I seem to always end up here down at the bottom, possibly off the screen. Barely on the screen, I believe. So what it says is take any horizontal. How about this one right here? This is the angle. It's called the angle of inclination of the line, in fact, and the slope is the tangent of that angle. So the punchline here is if theta is the angle of inclination, then tangent theta is the slope. Good. Let's quit there.